guess it's for you to find out.
All right, so if you look at what I posted, like I said, there's a lot of pages, but it's not overly difficult. All right, it's very simple, a lot of truth tables, a lot of symbols, a lot of truths and falses. All right, so we start off, what's a proposition? What's a proposition? Propose something, okay? Typically that's what you would think of when you see this. Now, when you propose something, normally is that proposition?
A solution to a problem.
Okay, solution to a problem. All right, what else? Sometimes when you propose something to somebody, it's in the form of a what? Question, not this. These propositions cannot be questions. These propositions are pure statements, all right? These are statements that can be true, statements that can be false. Okay? So these are just statements that are either true or false, but they can be both. A statement cannot be true and false. It either has to be true or it has to be false. Doesn't matter if it's false, it's still a proposition. A question or an opinion, it's not a proposition. Right? So, can I give you some examples? Real quick, based off of that definition of a proposition, so no questions. No opinion. And it also cannot be an instruction. All right. So we look at this. All men are mortal except me. Is that a proposition? Why not?
You.
It's a statement that's either true or false. That's all.
This is true. I am completely immortal. If that was true, this would be a statement. But because this part, if we left off the except me, except Mr. Easter, then yes. All. But because I added this piece, that's my opinion, okay? Or whatever you want to call it. But isn't it? If I was indeed true. Well, I guess in that respect, if I truly thought I was immortal, then it would be a statement. Okay? Now, the grass is green. Is that a proposition? Yes. Tell me your name. Why not? These are the ones that get a little tricky. Because this, we're not allowed to have an instruction. Tell me your name can be taken as an instruction. So these are the ones that can get tricky. Right? So that one I would consider an instruction. And therefore not a proposition. What is your name? Is that a proposition? That's a question, so it rules out the proposition. How about 7 is greater than 4? Proposition? That one's a proposition. 3 little birds. It's a statement. It's not a question. It's not an opinion. It's not an instruction. As odd as that is, that's a proposition. Doesn't have to make sense. Come back. It's kind of an instruction, right? It's telling somebody to do something. So, or a dog or a cat or something, telling something to come back. So that's an instruction. Can cow see color? Waiting for one of you to say no.
I did.
All right. So you get the idea. Now, there's your intro to some stuff. All right. These are the things that we're going to be working with. we're going to be working with statements, we're going to be working with propositions, we're going to be eventually working with compound statements. The good thing is, you've already worked with some of these compound statements, right? In geometry class, in other math classes, in last year's class, you guys have worked with some of these logics, right? So this is not really anything new, it's just putting it in a slightly different format. Now, when we look at this, propositions can be easily written using letters, and typical letters that go along with this are P and Q, or if you have more than those, R and S go along with it, all right? So, an example, if I let P be all dogs bark, and Q is 2 is the smallest prime number, those are statements, those are propositions. So we have P would be this, Q would be this. Then we would do something, okay? We can talk about what is the truth value. What is truth value? Truth. It's either true or it's false, okay? Truth value is it's either true or it's false, all right? So if we take a statement, say, all dogs bark, and I negate it. What happens when I negate a statement? So what did you do? You do the negative, you do the opposite, you add the word not in there. So a negation is just simply adding the word not, all right? So the negation of P would be exactly what she said. All dogs cannot bark, all right? Or all dogs do not bark. Or not all dogs bark. All of those are a negation of that statement, okay? 2 is the smallest prime number. How would you negate that? 2 is not the smallest prime number. Now, 2 is the smallest prime number. Is that true or false? That's true. 2 is not the smallest prime number. Is that true or false? It's false. All dogs bark. Is that true or false? True. It's actually false. There are breeds of dogs that do not bark. Okay. And it's not because they're mute, they just don't bark.
No,
You can't cut it off.
It's stone. I think one of the breeds is a Basenji. I could be wrong. Basinge. I don't know, I've never really had to spell it, I'm not sure. I think a Basenji does not bark. Well, all dogs will probably bark. Alright, so our first introduction to a truth table is this very, very simple truth table. And believe it or not, we've already done these things. Alright? So if I have a value and we negate it, if I have 2 and I negate 2, what do I have? Negative 2. If I negate a negative 2, what do I have? A negative of a negative 2 is back at 2. Negations in truth tables work the same way. Right? So, what did we say we had for options for a truth value for any statement P? P can be either what or what? True. True or false. So, if P is true, what is the negation of P? False. False. What is the double negation of P? True. True. If P starts off as being false, what's the negation of P? True. True. And then the double negation is back to false. So that's how truth tables work. That's how symbols work. All right? Now, you're going to see a negation a couple different ways. All right? When we did Venn diagrams, we saw a negation as that prime. All right? So if we remember when we said the union of P and not Q, all right? So this was the negation. So when we're dealing with Venn diagrams, our negation doesn't follow this symbol, it follows this symbol. They have the same meaning though. And a lot of the things that we do with our truth tables and all of the things that we're gonna do with our logic today, a lot of it can be related back to what you did with the Venn diagrams. Fair enough? Pretty easy stuff. Nothing too heavy too soon. Uh-oh. Compound statements. How do you think you're gonna make a compound statement? What's something? What did we just talk about? Not conditions. What were those statements called? Proposition. So a compound statement, what would a compound statement be? The combination or combining of propositions. Okay? So the compound statement is just a combination of or connecting of propositions. So a compound statement is made by connecting propositions. Now, keep in mind in the IB, you are not going to have to do like in biology, I think it is, where you have to give definitions of vocabulary words. This is just for your knowledge. You're not going to have to define any of these. Okay? It's just knowing what these are when you see them. So, couple compound statements. It is raining and I forgot my umbrella. It is raining or it is sunny. It is not raining and it is sunny. It is raining or it is sunny, but not both. Okay? Obviously, we could have thrown another one in there because sometimes it is raining and it is sunny. Or
It is raining or it is sunny.
what's what?
It is raining or it is sunny. It's out there.
Is different than it is raining and it is sunny. Okay? But in each one of those examples, what do you see? Okay? Conjunction. Which one is the conjunction? Which one is the conjunction? And. Or is not a conjunction. Only and. So and is the conjunction. Anytime you see the word and, it's a conjunction. So what's or? No? Oh, yes. All right. Conjunction. Conjunction is very simply when two propositions are connected by the word what? What did we just say? And. The logic symbol for and is easy to remember because it's almost like a capital A. It just doesn't have a crosswalk. It's a caret. Okay? It's an arrow that points. So it's just an arrow that points up. If you think about it, A, and if I were to connect that across, that would be an A. So it almost looks like a capital print A. Right? In symbols, if we have the two propositions P and Q, in symbols, it looks like P caret A, P hat A, whatever. All right? So your symbol, and I had to use the caret on this because my type doesn't like it. It actually should be full statement like that. Now, when we have this conjunction, we have two propositions. How many possibilities do you think we could have for the outcome? More than 50-50. More than two.
Three.
More than three.
5.
Not quite as many as 5.
4.
4. All right?
True, not true, not true.
Almost.
No, true, not
Well,
true, not true.
What are some options? What is an option for B?
True.
It could be true.
It's the not
Well, if B is true, what is an option for Q?
I do not. True.
True. But if B is true, does Q have to be true? No, it could be
False.
false. So those are two of the possible outcomes. Well, if P is not true, what is it?
False.
It could be false. And if P is false, then Q could still be true. And then if P is false, Q could also be false. And this is where it gets slightly tricky. Well, if P is true, Q is true, what about P and Q?
Yeah.
What's the value?
True.
True and true means
True.
true. True and false means
Yes.
false.
True.
False and true means false. False and false means
True is not doing
true is not doing so well. All right. So for a conjunction to be true, what has to happen?
It has to be both true.
Yes, both P and Q must be true. Okay. Now, I said this, a lot of these things can be represented in a Venn diagram. Where would this be in a Venn diagram? What do you mean in the middle? The shared part, the overlap, the intersection. Okay? That's where this conjunction is. Right? So signified by the overlap, the shared, or the intersection. Whichever way you want to think about that. All right? Sorry, 4 possible outcomes. So there's a conjunction. No matter what your propositions are, no matter what your statements are, you have 4 possible outcomes. First statement's true, second statement's true. First statement's true, second statement's false. First statement's false, second statement's true. First statement's false, second statement's false. You will see that pattern in every single truth table that we are going to do. The first 2 columns in all of your truth tables are going to be these exact values. Right? First true, second true. First true, second false. First false, second true. First false, second false. The first 2 columns are always going to be the same. What you do with those statements in that 3rd, 4th, 5th, 6th, whatever column, those are going to change. But the first 2 columns are always going to be the same. Right? Now, a disjunction. So a conjunction is and, a disjunction is or.
Disjunction.
So disjunction is or. This logic symbol. All right, the logic symbol for or is the upside down conjunction. So it looks like a capital V. All right? And symbols, if you have 2 statements, it's P, V, Q. All right? So the symbol for a conjunction okay. Conjunction looks like a hat, a caret. A disjunction is a V. And these are those symbols that I'm talking about. So you will see these types of symbols. You won't see the words, you'll see the symbols on your idea table. Or you will have to take the words and put them into symbols. What? No.
Okay.
Good. All right. Now, What about the truth? We did the truth table for the conjunction. How about the truth table for a disjunction? Well, ignore that. The columns are always the same. True, true, false, false. True, false, true, false. Always the same. In this house, in every single one, because they're all going to follow the same pattern. True, true, false, false, true, false, true, false. Every single one. Now, think about this, and think about this in terms of possibly your Venn diagrams. Or, we're dealing with the word or, a disjunction. It's P or Q. What is the true value when we have true, true?
True.
Okay, true. What is the true value when we have true, false? True. Why? Because it's either P or Q happening. Did either P or Q happen?
Yeah.
Yes. Well, what about false, true? Is that true or false? That's also true. And then what about false, false?
False.
That one's false. Okay? So it's one or the other. So for a disjunction to be considered true, what could we say?
True has to have.
So
Q has to have.
either P or Q or both must be true. So one or the other or both, either P or Q or both being true give us a true for the disjunction. Yes, you can shorten it up and say for a disjunction to be considered true, they both cannot be false. So, in a Venn diagram, what would this look like in a Venn diagram? So what would that be? Is that the union, the intersection? It's the union. Okay, so in a Venn diagram, that would look like the union. Now, there's a special case disjunction. It's called an exclusive disjunction. The exclusive disjunction, you will know it's an exclusive disjunction because it's going to say this can happen or this can happen, but not both. But not both. Okay? You will see it by or, but not both. Literally, you will see but not both. So it's got to have the symbol for the disjunction. It's got to have the V. And all it is a V with a line on it. It's an underscored V. Alright? So now, we got a conjunction, we got a disjunction, we've got an exclusive disjunction. So we got three symbols. All right, you should be able to fill out that truth table now. So I'll give you 15 seconds to fill out that truth table. Probably should be about. What are you thinking? That's because you're in pre. True, false. Now go to your state. Do you have? This is
Yeah, I'm going to the answer. Oh, yeah.
Put it up in preview, and that's why you keep losing it, because you don't have that PDF reader. Why, I don't know. We should have a PDF reader. All right, sorry. Did we get the truth table filled out? All right, so true, true, false, false, true, false, true, false. All right, so what about the third column? If it's true, true, what about this?
True.
False. False, but not both. So that one's false. How about this one? True. How about this one? True. And then that one's false. Now. Oh.
No, that one's false. And true. Wait, is the last one?
The last is false.
False.
False, because you can't have a true statement and true false statement. Okay? Now, so for this to be true, what can we say?
Both cannot be the same.
both cannot be true or false. Okay, so that's one way we can say that. Another way you can say that is it has to be one or the other, or both, or not, just not both. Okay? Now, on a Venn diagram, how would this look? Would this be the full union? Would it be?
It would be like an intersection.
Not the intersection. The intersection is the conjunction.
What's the other, the union?
The union is all of it, including the.
Would it be inside that?
What's that other one? It's a union.
So let's look at a picture. So conjunction would be this. Disjunction would be the whole thing. An exclusive disjunction
We just need two opposites.
would be
Yeah.
everything except the intersection.
Which is.
Okay? Everything but that intersection. Would be represented by the union minus the intersection. Because that's the both part, and we can't have the or both. All right, so there's your basics. You got a conjunction, disjunction, and an exclusive disjunction. Those are the three basics. Now, from there, we step up and we go into implication and equivalence. These are the ones that you've seen before. I know it doesn't sound like it, but in geometry, you use these all the time. All right? The compound statements where one proposition leads into another. Well, implication, when two propositions are joined by the words if and then. Okay, so if you see the words if and then you're looking at an implication. Is a double bar single arrow. A double bar single arrow, not a double bar double arrow. Okay. So a double bar arrow. It's an implication. It's probably the same one that you used before. Right? Shorthand. Now, what did you call these in geometry? Don't think too hard. Probably a lot of your geometry teachers called them if-then statements. Okay? So you have if-then statements, or some people call them conditional statements. Right? So that's what they're called. You got an if, then, or conditional statements. Right? If then statements sound really elementary, so big $10 word for this. When you get higher up in mathematics, we don't like that. We want to impress ourselves and we want to impress our colleagues, so instead of calling it conditional, we call it an implication. It implies. Makes it sound smart. Not really. All right? Now, in symbols, it looks just like that. Oops. Looks just like that. So we got one more to add to the list. We got an implication. Now, this is the weird part, and this is where mathematicians like to try to make themselves, again, sound a little more sophisticated than they really are. In a conditional statement, what did you call that if part? Everything after the if, between the if and the then. What is that? Do you remember? If something. What's a scientific word for if? Starts with an H. Hypothesis. And for every hypothesis, you have a what? What do you do at the end of your testing? Well, that's what you call this, whether you remember it or not. That's what you call this in geometry. You call the part behind the if the hypothesis, you call the part behind the then the conclusion. Well, now we are sophisticated IB students and we are higher than we think we are. Well, the part behind the if, okay, the part behind the if is called the antecedent. Big word. And the cue or the conclusion is called the consequent. Now, funny thing is, I think through all of my coursework in mathematics, I think I had one professor actually call it the antecedent and the consequent. I think all the others called it the hypothesis and the conclusion. Right? So that's fun. That's good. All right. So now we should be able to fill out at least the first two columns. Antecedent. A-N-T-E-C-E-D-E-N-T. So we know that the first one goes true, true, false, false. This one goes true, false, true, false. Now, if you start with a true statement and you end up with a true statement, what do we have? What's the result? If we start with a true hypothesis and with a true conclusion, we should have a true result. If I start with a true hypothesis and I end up with a false, then I end up with a false. But if I start with a false and my conclusion is true, or my consequent is true, conclusion is true, I actually end up with a true. And if I start with a false, and this one is false, then it's true.
What?
Two negatives equal positive.
Yes, they do. I guess you could think of it that way, yes. Two negatives is equal to positive.
In math. Harder to let people.
Well, that is good. That's all. Jeez. Okay, so when is an implication true? Unless you start with a true and go to a false, right? So it's always unless P is true and Q is false. So if the first is true, the second is false, then you end up with a false. Okay, so you have a true true, you have a false true, or a false false. So the only time that it's not true is when you start with a true value, but your consequence or your conclusion is false. Now, I will tell you the reason that it's good to use the word antecedent and consequent here, because our actual conclusion is the third column. It's not the second column. So that's why we use the word consequent and antecedent. All right? so we don't get mixed up. Now, on to equivalence. Equivalence is when two propositions are connected by the words if and only if. All right? If and only if. This one, the equivalence, is a double bar, double side arrow. So an implication is a double bar, single side arrow, and an equivalence is a double bar, double side. It's a double implication. Right, so it's a double implication. Now, again, looking at the truth table. True, true, false, false. True, false, true, false. Can't fit both of them. Can you guess what way this one is? It's gotta be, in other words, it's gotta be a two-way street.
False, true, false.
Not quite.
True, false, true.
True, false, false, true, very good. True, false, false, true. Now, let's see if I can squeeze this, it's not gonna fit, barely. Okay? If we compare it to the single implication, we start with true, ended true, we got true. If we start with true, ended false, we got false. If we started false, ended true, we got true. So if we started true, ended false, it was false. Well, if I start with true, end with false, we got false. But if I started with false and ended with true, I got true. But I can't, it's gotta go both ways. So it not only has to go one way, it's gotta go both ways. So when I start false and I go true, started false and went true, I got true. But then if I go back the other way, I started true and I got false. True and then false, it was false. So it's gotta, in other words, if I compare the double implication to this, these two in the middle are the ones that throw these off. Okay? So in a double implication or in equivalence, the only way for it to be true is when they are both true or both false. Okay, so either both true or both false. All right, we're not going to get through all of this. Hopefully I'll get through the next two tables.
Can you come back? So the deadlines of the limits, right? What? What? Oh my goodness.
Okay, so, well, that's pretty simple. What's the symbol for a negation? That sideways bar, okay, kind of looking thing. It's a button, like a broken bar. It's a horizontal and then a vertical bar. What's the symbol for a conjunction? It's right there. It's the A without the crossbar. What about for a disjunction? V. Exclusive disjunction. D with the bar underneath, implication. And then the equivalence. The double bar, double sided. Okay? Now, what it means to go through it, this one in words, not P, right? P in Q, P or Q, P or Q, but not both. If, then, and then if, and only if. And the if and only if falls in the middle of the sentence. It never starts off if and only if. You'll say the statement if and only if the second statement. All right? So when is this true? So the negation is true when P is false. The conjunction is true when both P and Q are true. This is the disjunction is when either P or Q are true. This is when P is true or Q is true, but not both. The implication is always true unless P is true and Q is false. And then the equivalence is true when P and Q have same value. Right? They're either both true or they're both false. Now, we can take all of those tables that we just did separately, and we can put them into one big table. And again, it's still true, true, false, false, true, false, true, false. Well, negate P. When P is true, that's false, false, true, true. And for lack of time, because I want to get through this, and I want to say one thing, we'll just fill it all out. True, false, false, false. True, 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 false. Ladies, I hope we're good. False, true, true, false. And then we got true, false, true, true. And then we got true, false, false, true. Now, put a little bit of worry at ease. No, you do not have to commit this to memory. Okay? Where is this? Your formula book. Just this. It doesn't tell you anything else, which is why we went through all that. It doesn't tell you what P means. It doesn't tell you what Q means. It doesn't tell you what the negation. Doesn't tell you to know those symbols. But the truth table, this truth table with all those values, is in your formula book. So you do not have to commit this to memory. So please don't think you have to try to memorize this. All you have to do is memorize what these symbols are. This is the part that you have to memorize. And what goes along with the word?
There's something you have to say about it.